Good morning, good afternoon, good evening, wherever you are. I'm Francesco and Cesarini. I'm the founder and technical director of Erlang Solutions, and I've been working with Erlang for the last 25 years. I started off when it was still a programming language and have had the privilege and honor to actually see it evolve into an ecosystem.
Hi, I'm Veronica Lopez. I'm a software engineer currently working at DigitalOcean, but also working as a release manager associate on the Kubernetes core team, which doesn't have to do a lot with functional programming, but you will see why this will be relevant during our talk.
So before we start, I wanted to thank everyone at Signify Technologies, for bringing together like-minded people, for a good cause. And the pandemic itself might stop us from seeing each other in real life, but it is not keeping us apart. And I think it's an important point to make that life goes on, and progress doesn't stop just because we can't go outdoors as much as we used to. So to our talk. So as the ecosystem has evolved, hardware has become more powerful. And trends and fashions have come and gone, and there have been tendencies often, in the progress we've made to go in and reinvent the wheel. And this reinvention of the wheel has sometimes been done pretty badly. And this causes, this whole kind of cycle causes the industry to take 2 steps forward and 1 step back, often stopping us from advancing as fast as it should. And I was giving a talk on the subject at Elixir Conf in Latin America. I think it was in Medellin last October. And there was another presenter sitting in the audience, Veronica. She was in the front row, furiously nodding at me. And in her talk, she had given a very similar message to mine. And as a result, we decided to pair up and give this joint talk. And I think it's always nice to work with like-minded people. So, Erlang has had an excellent track record at predicting the future. It was designed, as we usually say, for the internet age, although it predates the web. It was designed for multi-computers, although it predates them too. And with an intent to actually go out and find a tool to develop the next generation of telecom systems. They were the only systems back in the 80s which had to be distributed, scalable, and fault-tolerant. The computer science laboratory at Ericsson, came up with something truly unique, and it was a programming language. They were successful because when they set out to solve a particular problem, a problem of reliability and scalability of telecom networks, Erlang was the solution to that problem. And it has ever since kind of been a beacon for emerging programming languages. And the secret sauce and what actually makes it a beacon from other programming languages is its no-shared memory approach to concurrency, which in turn makes implementing distributed applications a very trivial task, because once you've solved distribution, you automatically get stability and reliability. And once you've got those, even scaling on multi-core architectures, it all very much comes out of the box. And I'll get into why now. But before doing so, let's just backtrack 20 years. I was an intern at the Computer Science Laboratory, and I was there with the co-inventors of Erlang. And more or less at that time, Java came out. And Klaus Wikström, as we call him, he's contributed to Erlang distribution, so he's basically added distribution to the semantics of Erlang. He created Nisia, which was one of the first distributed open source databases. It was a NoSQL database long before the term was invented. Clark invented a bit syntax, wrote the ASN1 compiler, and a long string of other achievements. He actually came in and he gave me a copy of the Java white paper, and the year was 1995. And when I was reading that white paper, I got a sense of deja vu. It was a virtual machine. There was a concurrency model, there was built-in memory management, and a garbage collector. Now, these are all things which we were working with, but it was nice to hear that others elsewhere were coming to the similar conclusion as us, because everyone was calling us crazy for wanting and even claiming that we could implement soft real-time systems on top of a virtual machine. They actually went in and believed that this extra layer was too slow. And the only way we can actually go in and implement scalable programs was using C. Now, what did they not see were the real costs, which was the loss of productivity gains and ease of development and the reduced maintenance costs. These were all things which in the early days of implementing and writing a product or even deploying it, you don't realize. And even more so, what they did not realize were the real costs of actually achieving resilience in the systems. It took us quite a while to figure out, but when you're running a program on a VM, you're actually reusing C code, the C code written when implementing the virtual machine itself. And I wish I'd come up with that explanation back then, because I think to quote Smalltalk Dave or Dave Thomas, he used this analogy with Smalltalk when trying to get it into an automotive industry. We should have used it back then in the telco space. And that Erlang is nothing other than a domain-specific language written in C. And that's what we should have told everyone telling us to use C. Well, we were using C. So besides being the crazy ones, besides being told it wasn't possible, there were 3 major projects using Erlang at Ericsson. It was packet-based switches, so the XT301. There were broadband solutions, so over copper cables, coaxial cables, fiber optics, and the predecessor of WiMAX. And mobile internet. So GPRS at Ericsson was the core parts of the GPRS network were at the time implemented in Erlang. And the lessons we learned from these projects was that you don't have to be the fastest, you just have to be fast enough. And where speed is of importance, however, was with time to market. Because those who released their product first were the ones who would go in and start getting their market share. And that had become critical, especially back in 1995 with the deregulation of all of the telecom markets, and also the breaking up of the monopoly in the US with all of the baby bells. Now, the JVM itself is a fine piece of engineering, but and especially back then, and that's today. But if we go back to 1995, Java itself at the time was in fact a product of a marketing department riding on the wave of the Microsoft antitrust wars. I think a lot has happened with all of the VMs, and there are lots of talks comparing and blog posts comparing the JVM to the Beam. And by the way, for those of you not familiar with the Erlang ecosystem, the Beam is today the most commonly used Erlang virtual machine. Now, there was one major difference which took me also a while to realize, between the JVM and the Beam, and that is that of threads versus concurrency. It's that of shared memory versus no shared memory, or mutable state versus immutable state. And the Beam and the JVM, ended up being built to solve very, very different problems. And usually I say, the JVM was built for speed, whereas the Beam was built for scalability and reliability. Or rephrasing this in words I've already used, one could say that the Beam was built for concurrency, and the JVM for parallelism. Now, concurrency, I think, here is key. Once you have a concurrency model based on no shared state, you can have distribution abstracting away from where things have executed. Now, assume you've got a process in London, where I live, and one in Mexico City, where Veronica is from. With a no shared memory approach, all of a sudden, you don't need to worry about thread safety. You don't need to worry about mutexes, to access critical sections of shared memory, or issues with network connectivity anymore. All of these become non-issues. Now, what distribution does is it will slow down the computation as a result of network latency. If you're in London and you need to compute something in Mexico City, it'll take time to cross the Atlantic and get back. But what it will slow down, however, is just one computation. If you're doing multiple computations in parallel, you will actually very quickly hit that threshold where you start seeing speed ups. And this is exactly the same concept to use when scaling your programs on multi-core architecture. You've got communication across cores, which is expensive, but your actual gains come when you start parallelizing your program. So, as I'm seeing it, the future of programming, whether we like it or not, is distributed. You need to start thinking about your mobile app, connecting to a serverless backend. And here, when it's so you use the buzzword serverless, all serverless means is that someone else is managing your servers. scratch under the surface, it still is a distributed system. So this is an article from the Ericsson's internal newspaper. I think it was dated 1996 or 1998. And Anywhere was one of the first open source products which Ericsson released. And what it did is it provided clusterware for dynamically scaling up and scaling down servers on existing office infrastructure. So I lived in Sweden at the time, and we had a very expensive Sun Microsystems workstations running Solaris and Sun OS on our desktops. And we used them for about 8 hours a day, Monday through Friday. With Anywhere, using a distributed file server and virtual machines, which would manage the infrastructure, when we went home for the day, the spare computing capacity on our desktop machines could be used to run other services, such as web servers for US users, for users in the States, who at the time would just be coming into work. As we were running it on a virtual machine, it just didn't matter if the computers were running Solaris, Linux, or Windows NT. And I think this was one of the very first examples I came across of orchestration and optimal use of computing capacity. And we see this as a predecessor to cloud computing. Cloud computing itself came about only 10 years later. And with it, came something which we often refer to as virtualization. Now, when we think of virtualization, it is something which, at least we in the Erlang community, have never really come to terms with. It certainly has a lot of use cases, but scalability, from our point of view, has never really been one of them. The Beam VM is a virtual machine which itself is an operating system on top of the operating system. It's an operating system which schedules lightweight processes. The hypervisor, running under the Beam, simulates the operating system, which in turn runs on a real operating system. And I think what I've always struggled to explain is that through virtualization, we add more layers, and the more layers we add between our software and the hardware on which it runs, the slower it will go. Not only will it go slower, it will also consume more resources and more energy. And adding these layers, at least for someone who's been used to fine-tuning the OS, fine-tuning the network, and fine-tuning the VM, it has always really, really felt weird. It was a bit like letting go of the control. We had a cutting-edge technology, which scaled vertically as well as horizontally. What was the need to add these layers, to the hardware? And and in fact, out of the Erlang community, we had a proof of concept. You'll see it on the right-hand side, called the Ling VM. And what it was doing is it was running an implementation of an Erlang virtual machine in the Zen hypervisor, running directly on the bare metal. So, an example of paravirtualization. And, paravirtualized Erlang, just like a modern container today, would run without the need of any hardware virtualization. The Ling VM took milliseconds to spin up. It would automatically set up and tear down network connections to other virtual machines based on software-defined networking principles and analyzing layer to layer free traffic. And it was all being orchestrated in a completely decentralized fashion. And this is not the future. This is the flow forwarding project from 1995. It was at the time sponsored by a company called Infoblox in the US, and it was all led by its founder, Stu Bailey. You can find the code. You can still find the code today on GitHub if you search for flow forwarding. So, going back very quickly, we talked about flow forwarding and horizontal scalability, but if we go back to vertical scalability, and I think this is also very relevant to the story, in January 2012, WhatsApp published a blog post, and they went in and announced that they had managed to achieve 2 million TCP/IP connections on a single Beam virtual machine. And they'd done so by, by fine-tuning the VM, the virtual machine, and making changes, as well as fine-tuning, changing FreeBSD. Now, for a company which at the time had a really, really small backend engineering team, when WhatsApp got acquired a few years later, they had 10 server-side engineers, which did all of the development, maintenance, and support of the system. So do your maths over how many there could have been back in 2012. I mean, for them, it was a huge achievement, but they invested in this achievement because what it did is it allowed them to cut both hardware costs and operational costs. And 3 years later, 3 years after they published this blog post in 2015, the changes which WhatsApp would work on had all been integrated into the Beam VM and become standard in most mainstream operating systems. And this is a blog post which talks about the Phoenix framework. Phoenix is, as many see, the successor to Ruby on Rails. It was written in Elixir, which is a language also running on the Beam VM. And they had managed to achieve 2 million TCP/IP connections out of the box. And what actually stopped them from going beyond these 2 million TCP/IP connections was actually the infrastructure on which they were running it on. It wasn't the operating system, and it wasn't the VM. And so, at this level, the vertical scalability was great, and at least, from my perspective, enough for probably 95% of all of the use cases I deal with on a day-to-day basis. But for the remaining use cases, you will need horizontal scalability. And then whenever I come across it, I always think back about flow forwarding, where we could spin off thousands of containers and tear them down and orchestrate them as needed, within seconds. And I see it very much as a predecessor to Kubernetes, which was way ahead of its time. Not even a lot of people at Infoblox or people working on the project actually realized the impact and the importance of what they were doing. So, I said it was ahead of its time because, whilst, flow forwarding happened at the same time as Phoenix, and Phoenix is today being used everywhere, it needed a different programming model and mindset. And back then, the world, I don't think, was ready for this mindset. It wasn't ready to build systems which would just completely scale out of the box.
That's right. And well, now if we fast forward to a few years ago, another hype wave we had to live through was that of containerization and Docker and all of this new, now very popular technologies. The idea of that you can orchestrate containers, while not wrong in itself and tightly coupled to the Beam mindset of let it crash, or even design your system to crash in a good way. But did it take us a step back? Kubernetes is a supervisor. Kubernetes restarts containers, and it sends messages to Docker instructing it to start, pause, or even stop containers. Even if you're not very familiar with containers, but you're familiar with the Beam, have you seen it at all before? Another sense of deja vu, right? So we already have an operating system on top of the operating system with the Beam. So do we really need containers and all of its tooling? The real positive thing Kubernetes and containers have contributed to is the movement towards cloud native, though. Cloud native is the way we have been doing things, not being bound to a particular operating system back in the days or cloud provider today, at least supposedly. Yeah.
So where is the future going and taking us? I think what we have here is, what we've put together, which represents an OSI. So think in terms of an OSI model for distributed computing, where we've gone in and broken up the whole stack into various layers, and we'll be coming back to these layers in the remainder of this talk. But where is the future taking us? Now, my view is kind of with cloud native applications, the developers abstracting away from the complexity of orchestration, underlying hardware, and all of the network layers. So what we really want to try to do, and what we're is to let the programmers focus on the business logic. Let them believe that they're coding an application for a single machine, following a particular programming model. And this programming model could be pub/sub, it could be event-driven, it could be actor-based. And their code now, thanks to the underlying infrastructure, so thanks to all of the layers we see here, which include the topology, the VM, the OS, and the network, would scale and be resilient without them having to change a single line of code. They would work, the state, would be shared transparently for the programmer across hosts. And, if a host goes down, services would be immediately be redirected to another host, which would have a replica of the data. And we've been putting all of this in our business logic and in our code. And I've always wondered, why is it not available today? Why is it not possible, and why don't we have it available today?
Yeah, the reason why I'm here today and why Francesco and I agree is because since most of my current work happens in the Go and cloud native ecosystem, I can see a similar deja vu effect that Francesco mentioned, but now with Go versus the Beam, and now especially with all the cloud native tooling versus the Beam. From a personal perspective, while Elixir is my favorite programming language, unfortunately or fortunately, most of my current professional work happens in the cloud native ecosystem, where I am lucky enough to not just be a user on the user level, but I'm also lucky enough to be part of important conversations with stakeholders and many important contributors way before the features or many new ideas make it into production, right? So the thing is that time and time and again, I see the wheel being reinvented in many of these conversations. But don't get me wrong, sometimes it is actually on purpose, because with all of this rise of Kubernetes and its tooling, one good thing that I see is that it has become like a democratization of distributed systems. So previously, like it used to be an area where only very specialized people could have access to, and now almost everyone can do it. But that comes with a lot of mistakes, which I don't see necessarily bad, but we have to listen to avoid repeating mistakes from the past. And the thing is that, as I said, sometimes it's on purpose, but sometimes it is not. And most of the time, it happens because people are not aware that similar tooling already exists. Similar tooling or similar concepts or similar work already exists. A lot of the people that I happen to work with, and that I'm very fortunate to work with because they are very talented, sometimes do not even know that the Beam is capable of these things. It's not that they even dismiss it, or that they don't think it's relevant or important, or that they don't like it. It just comes down to like being unaware of the powerful capabilities of the Beam. And yeah, therefore, currently, the result, if that happens like at the decision level area, the result is like currently developers end up using setting all their expectations on Kubernetes, instead of giving that responsibility to the lower layers or to the layers where it really makes sense for that matter. And as I mentioned in other talks, and Jose Valim has a great blog post about it, when people ask me whether it makes sense to use Kubernetes if you're already using the Beam or like vice versa, the answer comes down to the layers. Where is your problem at? And I think the OSI model for distributed computing happens to be very handy for this. Like every time that you are trying to solve something, you can do this quick exercise of like identifying where your main problem is, and then go ahead and decide. And well, following up with this idea, with the question of whether it makes sense or not, or even wondering if a language like Erlang or Elixir would still be relevant these days, given that tools like Kubernetes can now take care of it. And this is a real question that people ask me, especially given that these tools are supposed to be language agnostic. And don't get me wrong, that is totally the goal. And it would be like a preliminary step in the future of programming if we really achieved a state where all of this tooling, all of this Kubernetes, cloud native, containers, all that, were really, really, really agnostic in the terms, in the sense of that if we decided to switch from vendor to vendor, we would be realistically available to do it. These days, you can technically do it, but at the production level, it's still very painful. So basically, even if these projects were not thought with vendor locking in mind, unfortunately, that is still the case. Many times, not even with mean or deceiving purposes, but just because it's still very complicated. And so here I created a little table of to help you decide whether it makes sense or not on a practical level, like to shed some light into the main differences of what both things currently offer. And I decided to focus on the three most popular reasons why people would choose one or the other or both, right? So the main thing is the fault tolerance, the remediation. I think that nowadays Kubernetes, Beam, and all of these tools are very sought after for their fault tolerance and their resilience, their healing, all of these synonyms. So it is important to understand how they operate on the different tooling. For instance, in Kubernetes, it automatically restarts containers that fail, whereas the Beam restarts parts of the application. And how they supplement each other is that if we have a failure on the application level that makes it or parts of it unresponsive to health checks, for example, Kubernetes will act by saving the whole thing. On the other hand, having control of fault tolerance from a language level, just like as Elixir or Erlang would do, or other Beam languages without loss of generality, makes it easier to make more granular decisions to define a failure policy in general, So you can play with both. Then on the second element, we have service discovery, which is also, I think, one of the strongest suits of Kubernetes, because Kubernetes does this natively by automatically listing and managing the connections of the existing nodes. And if you're not familiar with the cloud native or Kubernetes vocabulary, is fine. Like, think of nodes as the instances, okay? So yeah, it automatically manages the connections of the existing instances, making them communicate and interact and all that. Additionally, cloud native tools like service meshes, for example, can have the dedicated infrastructure layer built right into the app. Now, the problem with this is very potential bloating of your application, but we can discuss that later. Whereas the Beam not necessarily has this from the beginning. It is absolutely possible to configure it, but then it doesn't come out of the box. There are some tools for the Beam languages, such as libcluster, for example, that provides a mechanism for automatically forming clusters of Erlang nodes, which is exactly how Kubernetes operates. It provides a publish and subscribe mechanism for cluster events so that you can easily be notified when cluster members join or leave. And projects, very popular projects like Partisan, already take advantage of this. So, I mean, it's completely possible, but it's yet another difference. And finally, the live code changes. Well, this is super relevant for many projects these days. However, the way Kubernetes and the Beam do it is very different. On the cloud native side, most of these tools rely on rolling updates, which if you're not familiar with this, basically like your entire installation or your entire system gets the updates in like little subsets or little batches. And once that one batch is done, we go on with the next one and with the next one, so that like obviously this provides no downtime, but also like a system to protect, like if a subset goes wrong, the rest of the subsets are still operating with the previous version, and like this allows very easy rollbacks in case something goes wrong. Whereas the Beam works with hot swap, and in my opinion, and many people that I currently work with, hot swap, well, super cool. Sometimes it's not even very necessary nowadays, although the reasons why it exists and is historically speaking, which is very relevant for our talk today, since, well, Erlang and all of these tools were created with telecommunications in mind. Well, hot swapping meant a lot in that context. So things like this hopefully will make you understand like the main differences, but also how interconnected they are, and how it is very easy to get confused and to try to make just one of them solve all of your problems. So there's this popular phrase, not just in computing, in everything, that says every tool's a hammer if you want it to be, which means that any tool can become whatever you want if you get creative enough. But in this case, I think we can use that creativity somewhere else. So please note that every time that I say Kubernetes, for the purposes of this talk, I'm also referring to all the current modern tools of the cloud native ecosystem. So with all of this in mind, and also please note how much I love the Kubernetes project, and that is why I'm so invested in it nowadays. In my opinion, Kubernetes was released a bit ahead of its time, not in terms of innovation or because people were not ready, but I think that people started using it in production environments when it was still very hard to install. For instance, like imagine just the installation process in like not so long ago, like 4 years ago, was still very painful, and some key features are still a work in progress. So this means that even if you can use them, you still have to be very aware of different things. There are many external tools to choose from that only cause more noise and decision fatigue at its best, and a very bloated and unnecessary complex system at its worst, which is basically the opposite of what we're trying to do here. Right, so Kubernetes is often used as a quick fix for leaky software, or it ends up being used as the only fault tolerance strategy for a remediation policy in a company or a project.
Yeah, so there's a question which came in, which is Beam, does Beam mean Apache Beam? No, Beam is the most commonly used, it's the prevalent Erlang virtual machine currently being used today. So yeah, so that's what we're referring to. It's unfortunate that there was an overlap in the name. So going back to what Veronica was saying, which is that of using Kubernetes, as a quick fix for leaky software, fault tolerance needs to be handled in all layers of the application, from your sequential code, within your process, within your supervision trees, and in the VM itself, on a container level, and also on the hardware level. So just because you're using Kubernetes doesn't mean it's not your responsibility anymore to deal with all of these layers. And also, there should be clear responsibilities. Developers should be focusing on the fault tolerance in the business logic of the systems. Architects who are designing the supervision trees should be focusing on fault tolerance on a supervision tree level and on a dependency level. DevOps should be focusing on orchestration and containerization and the VMs restart strategies. Cloud providers, on their hardware and network resilience. And whilst these examples we've been given right here focus on fault tolerance, I think they apply just as much to scalability. You'll need to manage scalability in all layers of the stack. It's not just something which which you can either bolt on as an afterthought or delegate just to one of the layers. So we wanted to share a tweet here from Kelsey, who also here seems to share our view. I'll give you a few seconds to read it. And I started seeing it like him a long time ago. Yeah, it was quite a while. It was a few years ago when I visited a company in the Bay Area. And I got a demo of their setup. They had Docker Compose, which allowed their containerized Elixir and Phoenix, based system to dynamically scale. And this company was using Docker at a time when probably no one should have been using Docker, and or at least no one should have been using Docker in production. And when I asked them about the monitoring, they probably showed me an app which had a really kind of colorful and fancy graph, and I saw this graph which looked to be stable at around 50. And I thought, there were transactions per second until I spotted the letters TPM. So they had gone in and put all of this unstable, over-engineered infrastructure in place to run a virtual machine, which at the time could handle 2 million TCP/IP connections, to cater for their 50 transactions per minute. And, and it was at this point when I kind of started realizing that, you want to abstract not only your programming model, but also all of your underlying infrastructures. And, I'd been very critical to the whole concept of serverless, but it was at that point when actually, when seeing, this is, that's when I realized a certain aspect of serverless, for me, all of a sudden started to make sense. And it figured out that all serverless basically means is that there is someone else who is going in taking care of your hardware and your infrastructure. So the idea we started coming up with was if they're taking care of your hardware and infrastructure, let them also take care of your scalability and your reliability.
Yeah, the hope is that in a few years, no one will be talking about Kubernetes and its tooling itself. And I say again, Kubernetes or any similar tool, any service mesh, any container orchestrator or very, very similar tooling, no one will be talking about them anymore on that level. Instead, we'll be discussing something built on top of it. We don't know what it is yet, which is part of the purpose of this talk, but will hopefully make more sense for everyone and make our lives as software professionals easier. Nowadays, unfortunately, the goal was and still is to abstract away the infrastructure, not because we say so, but because that would be the thing that would make everyone's lives easier. Instead, unwillingly, we suddenly converted every application developer into an infrastructure engineer, expecting them to know all of this tooling and be aware of all the implications of all of it. And it's just not sustainable.
So, back in the 90s, I was working on the very first release of the OTP middleware. It's a middleware used for Erlang-based systems. And if you listen to any of Jonas Moner's talks, it's the same middleware which actually inspired akka. And what we did is we abstracted the whole concurrency model out of your program by introducing workers and supervision trees in the programming model and giving the programmer libraries which contain all of the tricky parts which come with concurrency. And then multi-core came along, the Beam virtual machine, so the prevalent Erlang virtual machine of which is currently in use, allowed us to abstract the hardware. So no matter how many cores you had programmed, you programmed in a similar way using the same model we derived back in the 90s. And your system, because of the no shared memory approach, would automatically scale up. And abstraction is the key here again. As Veronica is saying, in the future, we'll be abstracting the infrastructure. And if we want to abstract the infrastructure, distribution and scalability will also have to be added to the programming models in a way that the programmer does not see, that they are actually, that they are implementing a concurrent system running on multiple computers, just so using the same approach we used in the 90s. And, we're heading in that direction with serverless, with stateful lambdas, and, I think lots of other frameworks, basing their concepts on the notion of reactive, event-driven, actor-based programming. But we've just started this journey, and there's no doubt that for every 2 steps forward, even here, we'll probably be taking a step back. And to minimize the amounts of steps we take back, we need to start providing a model, a programming model, which existing programmers and developers will find familiar, which does not reinvent the wheel, and which also does not result in a particular vendor lock-in. And the key here, is to use the abstraction layers, we've mentioned, to go in and actually hide the complexity.
So going back to the OSI model, here we have like a more detailed vision of how we see things. So what Francesco was saying is that all of this will result in software being cloud native, vendor independent, and clearly defined layers which can be hopefully swapped. The reason we are where we are today is that we do not have these clear boundaries, neither as developers nor as the tooling itself. Different layers are bound together, providing solutions that solve a particular problem, but cannot be reproduced or scalable. Just as Francesco was saying about the scalability, both in terms of the system itself, but how can all of your very hard work, I think, can be, it should be like plug and play in my imagination. Like ideally in the future of programming, all of this could be like plug and play. However, nowadays, like we see all of this tooling being used to solve a very, very particular problem, and then by the next problem, people need to start working like basically from scratch all over again, because everything is so complicated and the layers are very bound together.
So I was writing my second book, Designing for Scalability for O'Reilly, and I was feeling frustrated when you're writing the last 4 chapters, which were focusing on how to architect an Erlang-based system, or a system running on the beam, for both scale and resilience. And my frustration derived from the fact that there were no frameworks which would give us these features out of the box, which would give us scale and resilience out of the box. There were a lot of patterns, across systems, but there are almost no reusable libraries. And that is when I started realizing that we have all of these layers, which we're seeing right now in the slide, and that all of these layers were often overlapping each other. They're all getting entangled into each other. So any libraries and frameworks which were available would solve a very, very specific use case, but they would not be general purpose libraries. And take an old example, the React key value store NoSQL database as an example. I mean, it's still available as open source and still very much used in production today. Its distribution layer was based on the Dynamo principle implemented in React Core. And state using React Core could only be eventually consistent. It would only run on a fully meshed, non-changeable distributed Erlang cluster. And that meant that any business logic you wrote, which would run on top of React Core, had to also be implemented in Erlang, at least if it was to run on the same node. And the only other option you had was to use the database APIs, which is great, but then that would have bumped you up even higher on the application layer and basically tangled you in on an application layer. And I was being frustrated, but then I started looking at all of the other applications and frameworks which exist out there, and I came to a similar conclusion. Jonas Bonner has done something very similar with Akka Cluster. And all other distributed frameworks will solve certain problems, but they're not generic enough, and they're not configurable enough to solve probably 90% of all of the use cases.
And then again, a very similar problem is present today. There's so much tooling trying to solve very specific problems, and specifically talking about the cloud native ecosystem, but I am sure that you will find this problem in many other areas of computing these days, which is actually very frustrating. But going back specifically to cloud native, there is so much tools that it isn't a clear distinction between the subset of tooling or APIs required by different audiences, and strictly speaking of developer roles, or like software developing roles, such as infrastructure engineers, SREs, and the application developers themselves, and all the things in between, because all of these tools are still not very clear. And if you see different job postings, or even across companies, sometimes you will meet infrastructure engineers using certain tooling, but it's and only exclusive to their team. But there are still many other companies where the application developers are expected to master this tool aside from their day job. So that can become very complicated, and sometimes their responsibilities are blurred. And this obviously, regardless of the personal preferences, this doesn't foster productivity, because ideally every layer would be again strictly divided, and everyone would be able to focus on their problem, on their layer, and therefore be more productive. This is just the tip of the iceberg.
And indeed, it's the tip of the iceberg, which is the only thing the developer needs to see. As we've kept on saying throughout this talk, today's applications are completely bloated, and often they're monoliths. In the future, when you do a client-server call, the location where your callback is executed will become opaque. Start thinking cloud computing, fog, edge computing, as will be replication of the state across computers. And it is in our view that if we standardize APIs across all of the layers of this model for distributed computing, including the APIs for programming models, which we've given some examples here in the slide, but they're far from conclusive. So we think of stateful or stateless lambdas, event-driven programming, reactive, publish, subscribe, or even actor-based. Future systems would all be implemented on top of these APIs, even a simple create, read, update, delete application, which would allow us to move all of this functionality currently bloated in our systems into the underlying reusable layers. So I often think of it as an extended OTP, which today abstracts all of the concurrency and the tricky parts of the concurrency to handle vertical scalability and resilience. But it would also start taking into consideration distribution, hiding all of the challenges of distributed programming from the developer. So it would allow these models to become distributed and handle horizontal scale and no single point of failure out of the box. Think about writing callbacks for WhatsApp, but using an existing pub, sub, and presence API in the underlying layers for the message routing and the delivery. Think about not having to worry about scale and not having to worry about resilience, as a lot of the functionality of the underlying layers would actually fix this for you. And as your user base scales, without having to rewrite any of your business logic, you can go in and swap some of these layers with layers which are more specific to the pattern of your program. So this would be allowing Kubernetes to go in and do their magic, but without having to go in and expose it to the programmer. And in my view, this is the future of programming, one where business logic is built on pre-existing programming models, where distribution is hidden and state is shared by default. So you have distribution by default, but when you're developing, you're developing as if you're programming on one big computer. So it's a developer, you're programming for a single case, or as was 15 years ago, for a single core. And by default, your program will actually go in and distribute not only across cores, but also across machines. So, we're almost done. And in this particular case, your take-home lesson is ensuring you do not come up with something which takes us a step back when moving forward. And you do that by thinking about these layers. Divide your software stack accordingly when architecting it. And you go in, release these layers at open source, making sure they're reusable and interchangeable with each other, and not tied to a specific use case.
Yeah, I 100% agree with this. But also, in my experience, I've learned that as software professionals, and regardless of our backgrounds, our education backgrounds, or the projects that we're working on, it is always worth it to stop and take a look at history, see what is available, learn from the past mistakes, but also from the things that are really working still nowadays. Like even if they were written in the 70s, if they still work, how, like the popular saying, like if it ain't broke, don't fix it. But you can enhance it and extend it if it makes sense for you. It's not, I never want to come across as gatekeeping, but definitely take what already works and what didn't work at some point in time, and work from, like, starting from it. Don't reinvent the wheel. And I see that as the future of programming. Dividing your layers and just focusing on what makes sense, and not wasting our time and the things that are already solved by someone else, and probably in a very nice way already.
Okay. Thank you very much. I think we're out of time.
Nice.
Correct me if I'm wrong.
No, you're out of time, but there's a question in the Q&A section that if you'd like to, feel free to kind of pop in there and answer that.
So I have, yeah, it's a beam, mean Apache beam, and the answer was no. It's actually means it's a beam. It's a virtual machine in predominantly used in the Erlang ecosystem.
Perfect.
There are many virtual machines, but it's a predominantly used one. Yeah.
Okay, great. Well, in that case, then you can move over to the virtual hallway. So if anybody would like to head over and ask Francisco and Veronica any questions, I'll also put the link in the chat again to the virtual hallway. So feel free. They'll be heading over there to have a little chat and answer more questions. There we go.
Thank you very much. And you can also reach us on social. You can also reach us on social media. These are Twitter handles in case you have other questions and can't catch us in the virtual hallway. Thanks a million.